Correct. To summarize, on line 8, when I am using %p, that just means print a pointer value, so 0x something, I'm passing it s. Previously, when we used %s, printf knew to print not just the first character of s, but h, I, exclamation point, and then stop when it hits the \0. %p is different. %p tells the computer to go to that address, tells the computer to print that address on the screen. So this is where %s all this time has been powerful. The reason printf worked in week 1 and 2 and 3 was because printf was designed by some human years ago to go to the address that's being passed in, for instance, s, and print out character after character after character until it sees the null character, \0, and then stop printing it. So you're getting a lot of functionality sort of for free from %s. Today, we're using something much simpler, %p, which just literally prints what s is. And the reason we don't do this in week 1 is just because this is like way too much to be interesting when all you want to print out is hi or hello world or the like. But now what we're really doing is revealing what's been going on this whole time. And let me make one other example here. Let me go ahead and get rid of this variable here. And let me just print out a few things to make this same point. I'm going to print out not just s, like I did here, but let's go ahead and print out the address of every character in s. So let's get the first letter in s and get its address. And I'm going to do copy paste for time's sake, but not something I would do frequently. So let me print out the address of the first character, the second character, the third, and actually even the fourth, which is the \0, by doing this. So when I compile this program, make address, /address, I should see 2 identical values, and then additional values that are 1 byte away. In my diagram a moment ago, my addresses were arbitrarily 0x123, 124, 125, 126. Now it starts at, by chance, 0x402004, which is s. 0x402004 is the same thing as s because I'm just saying go to the first character and then get its address. Those are one and the same now. And then after that is 0x402005, 006, 007, because that is just like the diagram, go to the I, to the exclamation point, and to the null character. So all I'm doing now is using my newfound understanding of what ampersand does and what the star does, is I'm just kind of playing around. I'm poking around in the computer's memory, just to demonstrate there's no magic. It's all there very deliberately because I or printf or someone else put it there. Yeah? Really good observation. So it's indeed the case that hi, unlike 50, is kind of ending up at a very low address, not at the 0x7ff, wherever it was. That's actually because, long story short, strings are often stored in a different part of the computer's memory. More on that later today for efficiency. There's actually only going to be one copy of the word hi, an exclamation point, and the computer is going to tuck it at sort of the beginning of my memory. But other values like ints and floats and the like, they end up lower in memory by convention. But a good observation, because that is consistent here. All right, so a couple final details then on what's been going on here. Let me go ahead and claim that we implemented char star, or rather string, as a char star as follows. As of last week, we were writing this code. As of this week, we can now start writing this code because char star specifically, we invented in the CS50 library. But it turns out you've seen a way of inventing your own data types. Recall this thing here. We played around last time with data structures, or the struct keyword in C, and briefly the typedef keyword, which defines a type for you. And if I highlight what's interesting here, the way we invented a person data type last time was to define a person as having 2 variables inside of it, a structure that encapsulates a name and encapsulates a number. Now, even though the syntax is a little different today because of the star thing, notice that this could be a similar application of that idea. If I want to create a type called string, highlighted in yellow here, then I use typedef to make it defined to be char star. So this is literally all that has ever been in CS50.h. In addition to those prototypes of functions we've talked about, typedef char star string is a 1-line code that brings the word string as a data type into existence. And that's all that's ever been there. But the star, the char star, is just too much in week 1. We wait until this point to sort of peel back that layer. Are any questions then on what a string is, what star or the ampersand are doing? Yeah? Oh my God, massive spoiler. But yes, if that is that why when you compare two strings, as I briefly did, or almost did, problems arise. And in fact, yes, last week we used str compare, strcmp, for a very deliberate reason, because yes, the spoiler is I accidentally would have compared two addresses in memory, not the strings at those addresses. Other questions here? No? All right, well, before we give ourselves maybe a 10-minute break here, we have lots of pieces of paper. If anyone wants to come on up and play with this big stack of Post-its, if you want to make your own 8x8 grid of something to share with the class, if you're artistically inclined, come on up. Otherwise, let's take 10 minutes, and we'll return after 10. All right. So let's come back to this question of how we can start to use these pointers and these addresses ultimately in an interesting way. The goal ultimately next week is going to be to use these addresses to really stitch together more complicated data structures than just persons like last week, or candidates in the context of like an electoral algorithm, if you will, and actually really use our memory in the most versatile way to represent not just images, but maybe videos and other two-dimensional structures as well. But for now, let's come back to this address example. Whittle it down to just a hi initially, and see what's going on again here underneath the hood. So let me re-add the CS50 library just so we use our synonym for a moment. That is the word string. And I'll redefine s as a string. And what I didn't mention before is that these double quotes that you've been using for some time are actually a little special. The double quotes are a clue to the compiler that what is between them is in fact a string, as we now know it, which means the compiler will do all the work of figuring out where to put the h, the I, the exclamation point, and even adding for you automatically a \0. And what the compiler will do for you too is figure out what address all four of those chars ended up at and store it for you in the variable s. So that's why it just kind of happens with strings without using ampersands or even stars explicitly. But the star at least has been there because, again, string is just synonymous now with char star. It's not really as readable, but it is now the same idea. So I'll leave string in place just to do something sort of week one style here for a moment. And let's go ahead and print out a few characters. So I'm going to use %c this time. And I'm going to print out s bracket 0. And then I'm going to print out s bracket 1 and s bracket 2. Literally doing sort of week 3 style from last week, a printing of every character in s as though it were an array. So /address should give me hi exclamation point. And if I really want to get curious, technically speaking, I could print out one more location. And let me go ahead and recompile, make address, /address, and there is, it would seem, the \0. I'm not seeing 0 because I didn't type literally the 0 char in ASCII. It's literally 8 0 bits, which are technically unprintable, if you will, in printf speak. And so what I'm seeing here is like a blank symbol that just means there is something else there. It's apparently all 8 0 bits. But they are there, even though we're not seeing them literally right now. Well, let's go ahead and peel back one of these layers. And let me go ahead and get rid of the CS50 library and get rid of, therefore, the word string, because, again, henceforth, it's just char star. Nothing else is different. I'm going to now do make address, /address, and it's the same exact thing. And now let's just focus on the hi rather than even worry about that. So I'm going to recompile it one last time. And now I have hi exclamation point. Well, it turns out that the array notation we used last week was technically some of this syntactic sugar, sort of a neat way to use syntax in a useful way. But we can see more explicitly today what the square brackets for a string is actually doing. Let me go ahead and do this. Let me adventurously say I want to print out not s bracket 0, but I want to print out whatever the first character of s is. So to be clear, what is s now? It's the address of a string. OK, but what is s really? S is the address of the first char in a string. And again, that's sufficient for defining a string because eventually the computer will see that there's a \n at the end of it. So s is specifically the address of the first character in a string. So that means, using my new syntax, if I want to print out that first character, I can print out *s. Because recall that star is the dereference operator. When you don't repeat the word char, you don't repeat the word int, you just use the star here. That means go to that address. Similarly, if I, in my sort of newfound knowledge of how strings work, know that the h comes first, then the I right after it, then the exclamation point, then the \0, contiguously, 1 byte apart, I could kind of start to do some arithmetic. I could go to s plus 1 byte and print out the second character. And I could print out whatever's at s plus 2. In fact, doing what's generally known as pointer arithmetic, literally treating pointers as the numbers they are, hexadecimal or decimal, doesn't really matter. It's still just numbers. And go ahead and add 1 byte or 2 bytes to them to start at the beginning of a string and just kind of poke around from left to right. So this now is equivalent to what we did last week using square bracket notation. But now I'm re-implementing that same idea with this sort of lower level plumbing, understanding ampersands and stars now a little bit more. So if I remake this program and do /address, I should still see HI exclamation point. But what I'm really doing is just kind of demonstrating, hopefully, my sort of understanding of what really is going on in the computer's memory. Now, programmers who are maybe trying to show off might actually write this syntax. I think the more common syntax would be what we did last week. S bracket 0, S bracket 1, Y. It's just a little more readable. And like we don't need to sort of brag about or care about this underlying representation. The square brackets last week were an abstraction, if you will, on top of what is lower level math. But that's all that's going on underneath the hood. We're poking around from byte to byte to byte. All right, let me pause here, see if there's any questions on that one. Any questions on this? Let's do one more then, just to demonstrate that this is not even specific to strings. Let me go ahead and get rid of all of this, and let me give myself an array of numbers like I did last week. So if I'm going to declare all the numbers at once using this funky curly brace notation, I can do like 4, 6, 8, 2, 7, 5, 0. So 7 different numbers inside of an array that's automatically initialized like this. I don't, strictly speaking, need to say 7. The compiler's smart enough to figure out how many numbers I put with commas between them. And that just gives me an array containing 4, 6, 8, 2, 7, 5, 0. So it turns out I can print each of these numbers in the familiar way. I can do a printf of %i, \n, and I can print numbers bracket 0. And let me just do some quick copy paste just to print the first 3 of these. Theoretically, that should print out 4, 6, 8, and so forth. But I can do the same sort of manipulation, understanding what pointers now are using pointer arithmetic. So let me actually unwind this and just go back to one printf. And instead of printing numbers bracket 0 like I might have last week, let me just go and print out whatever is at that address. So asterisk numbers. Let me then print out the second digit, which is going to be whatever is at numbers plus 1. And then let me do this further and do whatever's at numbers plus 2. And if I really want to repeat this, let me do it 4 more times and do what's at location 3, 4, 5, and 6. And that's 7 total numbers because I started counting at 0. So let me just quickly run this. Make address, /address. There are those 7 digits being printed. But there's something subtle but also kind of useful here. Each of these digits, 4, 6, 8, 2, 7, 5, 0, is an int. Why? Because I made an array of integers. But think back. How big is a typical integer, have we claimed? 4 bytes, or 32 bits. So it's worth noting that I don't really need to worry about that detail. Notice that I did not do +4, +8, +12, +16, +20. Right? I, the programmer, strictly speaking, don't need to worry about how big the data type is. This is the power of pointer arithmetic. The compiler is smart enough to know that if you add 1 to this pointer, that is the same as saying go one more piece of data, not just 1 byte. So if it's an int, move 4. If it's a second int, move 8. If it's a third int, move 12. Pointer arithmetic sort of handles that annoying arithmetic for you. So you can just think of this as a number after a number after a number that are back to back to back, but not 1 byte apart, but 4 bytes apart. Which is only to say +1, +2, +3 works no matter the data type. Why? Because the compiler knows what type of data you're talking about. Now there's one other detail I should reveal here that I've kind of taken for granted. In the past, I was using double quotes to represent strings. And I claim that the compiler's smart enough to realize that, oh, if I have double quote hi, that means it's an array of HI exclamation point and then the \0. Notice this usefulness. It turns out that you can actually treat arrays as though the name of the array is itself a pointer. And this is actually going to be something useful in upcoming problems when we want to pass arrays around in the computer's memory. Notice that, strictly speaking, on line 5, there's no pointers going on. There's no star. There's no ampersand. There's nothing new there. And yet, instantly, on line 7, I'm sort of pretending that it is the address. And this is actually OK. It turns out that an array really can be treated as the address of the first element in that array. The difference is that there's no secret \0 anywhere. Like, this is just part of the phone number here, the ending in 0. That's not like a special \0. So this is something we're going to take advantage of, too, before long. There's this sort of interrelationship between addresses and arrays that just generally allows you to treat one as though it is the other. But the math is taken care of for you. Or any questions then on this before we start to solve some bigger problems? Yeah? Potentially, if you go beyond the end of an array, you might get a segmentation fault. The problem is that that symptom is sometimes non-deterministic, which means that sometimes it will happen, sometimes it won't. It often depends on how far off the end of the array you actually go. You'll often not induce a segmentation fault if you just kind of poke a little too far, but if you go way too far, it quite likely will. But we'll give you a tool today, actually, for detecting and solving exactly that kind of situation. So let's go ahead now and do something a little different in code, but that actually comes back to that spoiler from earlier. Let me go ahead and create a program called compare.c. And in this program, I'm going to go ahead and allow myself the CS50 library, not so much for string, but so that I can actually use getInt still, which is way easier than the way we'll see that C normally lets you get input. Let me give myself standard io.h, do an int main void, not worrying about command line arguments today. And let me go ahead and get an int I using getInt and ask the human for the value of I. Then let me give myself an int j, ask the user for another int, calling it j. And then let me go ahead and kind of naively, but to your point earlier, if I equals j, then let's go ahead and print out something like same \n. Else, let's go ahead and print out different if they are not, in fact, the same. So that would seem to be a program that compares the value of two integers. All right, so let's go ahead and run make compare. So far, so good. /compare. OK, I will be 50. J will be 50. They're the same. Let's do it once more. I will be 50. J will be 42. They are different. So far, so good in this first version of comparison. But as you might see where I'm going with this, let's move away from integers. And let's actually change these things to strings. So I could do string s over here, get string s over here. Then I could do string t over here and get string over here, asking the user for t this time here. And then I can compare the two. If s equals t, and this is a common convention. If you've used s for a string already, you can use t for the next one, at least for simple demonstrations like this. I'm going to compare the two, just like I did for ints, which worked great. Make compare. So far, so good. /address. Sorry, wrong program. /compare. Let me go ahead and type in something like hi, exclamation point, and by, exclamation point, which, of course, should definitely be different. Let me run it again with hi, exclamation point, and hi, exclamation point. Different. Maybe I messed up. Let's maybe do lowercase. Maybe that'll fix. But no, those two are different. So to come back to what I described as a spoiler earlier, what's the fundamental issue here, to be clear? Why is it saying different, even though I'm pretty sure I typed the same thing twice? Yeah. Yeah, this is where it's now useful to know that string has been an abstraction, a training wheel, if you will. And if we take that away, still use getString because that's convenient still. But if I change string to be char star, it's a little more explicit as to what s and what t are. S is a pointer to a char. That is the address of a char. T is a pointer to a char. That is the address of a char. Specifically, the first character in S and the first character in T, respectively. So if I'm comparing these two, it should stand to reason that they're going to be different. Why? Because S might end up here in memory, and T might end up here in memory. Each time I call getString, it is not smart enough or advanced enough to know that, wait a minute, you typed the same thing. I'm just going to hand you back the same address. That doesn't happen because we did not design getString that way. Each time I call getString, it returns, apparently, a different copy of the string that was typed in, a high over here and a high over here. They might look the same to the human, but to the computer, they are different chunks of memory, and therefore at different addresses. And here, too, we can reveal what is getString returning. Well, up until today, it was returning a string, so to speak. That's not really a thing. Technically, what getString has always been doing is returning the address of the first char in a string, and trusting that we put a \0 at the end of whatever the human typed in, and that's enough now for printf, for strlang, for you, to know where a string begins and ends. So getString has actually always returned a pointer. It has not returned a quote unquote string per se. But there are functions that can solve this comparison for us. Recall that I could do something like this. I could actually go in here and I could, let's see, where was it? So if I include strCompare here and use it to pass in two values, s and t, let's see now what happens when I make compare. Implicitly declaring library function strCompare with type int, and well, there's a star. So you might have seen this error before, and you might have ignored most of it, but there's some evidence of stars or pointers going on here. It looks like I didn't include the string.h header file, so that's an easy fix. Include string.h, which, despite its name, does not create a data type called string. It just has string-related functions in it, like strCompare. Let's make compare again. Now it compiles, /compare. Now let's type in high exclamation point, and even the same thing again. These are now, oh, I used it wrong. OK, user error. That was supposed to be impressive, but it's the opposite. What did I do wrong? What did I do wrong? Here, yeah. Yeah. Yeah, it returns three different values. 0 if they're the same. Positive one becomes before the other. Negative if the opposite is true. I just forgot that. So like I did last week correctly, if I want to compare them for equality, per the manual page, I should be checking for 0 as the return value. Now make compare, /compare, enter. Let's try it one last time. High and high. OK, now they're in fact the same. And just in, thank you. And indeed, not that it's returning same all the time. If I type in high and then by, it's indeed noticing that difference as well. Well, let me go ahead and do one other thing here. Let's do one other thing. Let me go ahead now and just reveal more pictorially what's going on. Let's get rid of the string comparison, and let's just print these things out. The simple way to print this out would be with %s. And again, %s is special. Printf knows take in an address and start there. Print every character up until the \n. So let's just hand it s and do that. And then let's do one more, %s, t. This is, again, sort of a mix of week 1 and this week, because I got rid of the word string. I'm using char star, but I'm still using printf and %s in the same way. Let me go ahead and run compare now. And if I type high and high, I should see the same thing twice. So they look the same. But here now we have the syntax today to print out the actual addresses of these things. So let me just change the s to a p, because p means don't go to the address and print it. It means just print the address as a pointer. So make compare, /compare. And now let's type in high and once more. And I should see indeed two slightly different addresses given in hexadecimal. One's got a b at the end, one's got an f at the end, and they are indeed a few bytes apart. So this is just confirming what our suspicions have actually been. So what does this mean perhaps in the computer's memory? Well, let's kind of take a look. I've zoomed out so I have a little more squares to look at at once. Here might be s in memory when I do string s equals, or char star s equals. I get a variable that's of size 1, 2, 3, 4, 5, 6, 7, 8, because I claimed earlier that on modern systems, pointers are generally 8 bytes nowadays, so they can count even higher. And inside of the computer's memory also might be high. And I don't know where it ends up, so for the sake of discussion, it ended up down here. That's what was free when I ran the program. HI exclamation point \0. Maybe it ended up, for the sake of discussion, at 0x1, 2, 3, 4, 5, and 6. So to be clear, what is s storing once the assignment operator copies from right to left? What is s storing if I advance one more slide? Yeah. 0x123, the presumption being that if a string is defined by the address of its first char, and that address of its first char is 0x123, then that's indeed what should be in the variable s. And so technically, that's what's been happening with that assignment operator from right to left. GetString indeed returns a string, so to speak, but more properly, it returns the address of a char. What's been then copied from right to left using that assignment operator all these weeks is indeed that address. Now, technically, we don't really need to care about where these addresses are. It suffices to just think about them sort of referentially. But let's first consider where t might be. T is just another variable that I created on my second line of code. Maybe it ends up there, maybe somewhere else. For the sake of discussion, I'll draw it left and right. Where did the second word end up that I typed in? Well, suppose the second copy of hi ended up at 0x456, 457, 458, 459. What ended up in t? I'll pluck this one off myself. 0x456, presumably. And so this is now a pictorial representation of y. And let's abstract away everything else. When I compared s against t using equal equals, based on the picture, they're obviously not the same. One is over here, one is over here. And per a moment ago, one is 0x123, the other is 0x456. Yes, technically they're pointing at something that's the same, but that just reveals how stir compare works. Stir compare is apparently a function that takes in the address of a string as its argument and the address of another string as its argument. It goes to the first character in each of those strings respectively, and probably has like a for loop or a while loop, and just goes from left to right comparing, looking for the same chars left and right. And if it doesn't notice any differences, boom, it returns 0. If it does notice a difference, it returns a positive or a negative value. And that's very similar, recall, to how we implemented string length ourselves last week. I sort of used a for loop. I was looking for a \0. Stir compare is probably a little similar in spirit, looping from left to right, but comparing this time, not just counting. Are any questions then on string comparison and why it is that we use stir compare and not equals equals? Yeah? Do pointers have addresses? Yes. So we won't do that today. But I could actually use the ampersand operator on s or on t. That would give me the equivalent of a char star star that itself could be stored elsewhere in memory. That's where it ends. We don't sort of do that recursively forever. There's star and there's star star. But yes, that is a thing. And it's very often useful in the context of like two-dimensional arrays, which we haven't really talked about. But that is a feature of the language too, but not today. Good question. All right, so what might we now do to take things up a notch? Well, let's go ahead and implement a different program here that maybe tries copying some values just to demonstrate this. Let me open up a file called, how about copy.c. And I'm going to start off with a few includes. So let's include the CS50 library just so we have a way of getting user input. Let's include, how about standard IO as always. Let's preemptively include string.h and maybe one other in a moment. Let's do int main void as before. And then in here, let's get a string from the user and just call it s for simplicity. And heck, we can actually just call this char star if we want, or string, since we're using the CS50 library. But we'll come back to that. Let's now make a copy of s and do s equals t using a single assignment operator. And then let's check something like this. Let's go into the first character of t, which is t bracket 0. And then let's uppercase it using that function that we've used in the past of toUpper, t bracket 0 semicolon. And actually, I should go back up here. If I'm using toUpper, or if you've used toLower, or isUpper, or isLower, might not remember this offhand, but it was in another header file called ctype.h. There was a bunch of helpful functions in that library as well. Now, at the very last line of the program, let's just print out what both s and t are by simply printing out %s for each of them. And t is %s also. Not %t, of course. And let's see what happens here. So let me make copy. Oh my god, so many mistakes. What did I do wrong? Oh, OK, that was unintended. String t equals s, sorry. So I'm creating two variables, s and t respectively, and I'm copying s into t. Make copy, enter. There we go. /copy. And let's now type in, for instance, how about hi, exclamation point, in all lowercase this time. And now what gets printed? I don't think that's what I intended, so to speak here, because notice that I got s from the user, so that checks out. I then copied t into s, which looks correct. That's what we always use assignment for. Then I uppercased the first letter in t, but not s, at least in my code. Then I printed s and t, and then notice, apparently, both s and t got capitalized. So if you're sort of starting to get a little comfortable with what's going on underneath the hood, like what's the fundamental problem here? Why did both get capitalized? Why did both get capitalized? Yeah, over here. Yeah, they're representing the same address. So C is really literal. If you create another variable called t and you assign it the value of s, you are literally assigning it the value in s, which is like 0x123 or something like that. And so at that point in the story, both s and t presumably have a value of 0x123, which means they technically point to the same hi exclamation point in memory. Nowhere did I tell the computer to give me a copy of hi exclamation point per se. I literally said just copy s. So here's where an understanding of what s literally is kind of explains the situation. I'm only copying the pointers. So what actually went on in memory? Let's take a look here at this grid. If I created s initially, maybe it ends up here, and I created hi in lowercase, and it ended up down here, then the address was, again, like 0x123, 4, 5, 6. 0x123 is what's in s. If then I create a second variable called t, and I call it a string, aka char star, maybe it again ends up here. But when I copy s into t by doing t equals s semicolon, that literally just copies s into t, which puts the value 0x123 there. So if we now abstract away all these numbers and just think about a picture with arrows, what we've drawn in the computer's memory is this. Two different pointers, but storing the same address, which means the breadcrumbs lead to the same place. And so if you follow the t breadcrumb and capitalize the first letter, it is functionally the same as copying changing the first letter in the version s as well. So what's the solution then to this kind of problem? Like, even if you have no idea how to do it in code, like, what's the gist of what I really intended, which is I want a genuine copy of s called t. I want a new hi exclamation point backslash 0. What do I need to do to make that happen? Thoughts? So there is a function called strcpy, strcpy, which is a possible answer to this question. The catch with strcpy is that you have to tell it in advance not only what the source string is, the one you want to copy, you also need to pass in the address of a chunk of memory into which you can copy the string. And here's one thing we haven't seen yet, and we need one more building block today, if you will. We haven't yet seen a way to create new chunks of memory and then let some other function copy into them. And for this, we're going to introduce something called dynamic memory allocation. And this is the last and most powerful feature perhaps today, whereby we're going to introduce two functions, malloc and free, where malloc means memory allocate, which literally does just that. It's a function that takes a number as input. How many bytes of memory do you want the operating system to find for you somewhere in that big grid? It's going to find it, and it's going to return to you the address of the first byte of contiguous memory back to back to back. And then you can do anything you want with that chunk of memory. Free is going to do the opposite. When you're done using a chunk of memory that malloc has given you, you can say free it. And that means you hand it back to the operating system, and then the operating system can use it for something else later. So this is actually evidence of a common problem in programming. If your Mac, your PC, has ever been in the habit of starting to get like really, really slow, or it's kind of slowing to a crawl, heck, maybe it even freezes, one of the possible explanations could be that the program you're running by Apple or Microsoft or whoever, maybe they're using malloc or some equivalent, asking the operating system, Mac OS or Windows, for give me more memory. I need more memory. The user's creating more images. The user's typing a longer essay. Give me more memory, more memory. If the program has a bug and never actually frees any of that memory, your computer might end up using all of the available memory. And honestly, humans are not very good at handling corner cases like that. Very often, programs, computers just freeze at that point or get really, really slow because they start trying to be creative when there's not enough memory left. So one of the reasons for a computer really slowing down might be calling malloc a lot or some equivalent, but never freeing it, which is to say you should always use these two functions in concert and free memory once you are done with it. So let me go ahead and do this in code and solve this problem properly. Let me go ahead and do this. Before I copy s into t using something like strcpy, I first need to get a bunch of memory from the computer. So to do that, let's make this super clear that we're dealing with pointers. So I'm going to change my strings to char stars for both s and t. And what I technically am going to store in t is the address of an available chunk of memory. To do that, I can ask the computer to allocate memory for me. And how many bytes? If I want to create a copy of hi exclamation point, I need how many bytes? Good, 4, because I need the h, the I, the exclamation point, and additional space for the \0. It's up to me to understand that and ask for it. It's not going to happen magically. Nothing does in C. So I could just naively type 4 there, and that would be correct if I type in hi exclamation point or any other 3-letter word or phrase. But to do this dynamically, I should probably do something like strlen of s plus 1. For the additional null character. Recall that string length does it in the sort of the English sense. It returns the length of the string you see. Plus 1 also takes into account the fact that I'm going to need that \n. Now let me do this old school style first. Let me go ahead and manually copy the string s into t first. So for int I equals 0, I is less than the string length of s, I plus plus. Then inside my for loop, I'm going to do t bracket I equals s bracket I. But actually, I want the null character too. So I want to do the length of the string plus 1 more. And heck, I think I learned in optimization last time. If I'm doing this again and again, I could really do n equals strlen of s plus 1, and then do I is less than n, just as a nice design optimization. I think this for loop will actually handle the process then of copying every character from s into every available byte of memory in t. Or I could get rid of all of that and take your suggestion, which is to use strcpy, which takes as its first argument the destination and its second argument the source. So copy from right to left in this case too. That's going to do all of that automatically for me as well. Now I think I'm good. I can now capitalize safely the first character in t, which is now a different chunk of memory than s. And then I can print them both out to see that one has not changed, but the other has. So make copy. All right, what did I do wrong? Implicitly declaring library function malloc ... So we've seen this kind of error before. What is, even if you don't know quite how to solve it, what's the essence of the solution? What do I need to do to fix this kind of problem involving implicitly declaring a library function? What did I forget? Yeah. I need to include the library. And I could look this up in the manual, or I know it off the top of my head. I just forgot it. There's another library we'll occasionally need now called standard lib, standard library, that contains malloc and free prototypes and some other stuff too. All right, let me just clear this away and do make copy one more time. Now I'm good. /copy, enter. All right, s, I'm going to type in hi lowercase, t, and s. Now come back as intended. S is untouched, it would seem, but T is now capitalized. All right, any questions then on what we just did in code? Yeah.